Well, if two integrals are good, then three integrals must be even better. So this section will take a look at triple integrals. It's going to follow the same pattern as double integrals, except one more. The one little difference, and you can see the whole story in the PowerPoint notes, is that when you do triple integrals, you're going to work inside to outside, but the inside limits of integration are going to be functions of x and y. The next level will be functions of x. The next level will be constants. So you notice up here, here's the area that you're integrating over, right? There's your dv. The x's go from a constant to a constant. The y's go from two functions of x. The z's go from two functions of x and y, from one to the other. And so then you end up with an f of x, y, z, right? Three variables, dz, dy, dx. Right? The first set of limits of integration are functions of x and y. These are functions of x. Those are constants. Right, how does all this work? Well, from the inside out. So this one starts with a dy. This one is given dy dx dz. And so let's start from the inside. When we integrate with respect to y, the x and the z are treated as constants, so we end up with a 6xy squared z over 2, right, divided by the new power, and that gives us 3xy squared z evaluated at what? Y equals 1 and y equals 0. So when you evaluate it at y equals 1, you get 3xz. When you evaluate it at y equals 0, it just wipes it out. All right, so now the second step is integrate with respect to x. So we'll integrate 3xz with respect to x from -1 to 2. Right, bump the power up by 1, divide by the new power, so I get 3x squared z over 2 at x equals 2 and at x equals -1. So this will give me a 3 times 2 squared times z minus 3 times -1 squared times z all over 2. All right, so 4 times 3 is 12, so I get 12z. This will give me a positive 1, so minus 3z equals 9z over 2. All right, now we got to integrate that with respect to z. So now I'll integrate from -1 to 1 of 9/2 z dz. Right, so that gives me 9z squared over 2 times 2, which is 4, evaluated at 1 and at -1. So I get 9 times 1 squared over 4 minus, if I put a -1 in for z, -1 squared is just 1, so I get minus 9 times 1 over 4 again. I end up with 0. Is every triple integral 0? Oh no, this one just happens to be. So if you're calculating volume, same amount above the plane as below it. All right, let's take a look at an example with a volume of a solid. I have a volume of the solid formed in the first octant, right? When you take the x, y's, and z's, you end up, instead of with 4 quadrants that you would have if you had the xy plane, you end up with 8 octants. The cylinder is z equals the sine of y. It's true for y values between 0 and pi, sliced by the planes y equals x and x equals 0. So x equals 0 is going to form the bottom of this object, right? That's why it's flat on the bottom. And y equals x is going to form this side over here. And if that's true, if y and x are the same thing, and it goes to y equals pi, that's how I get the y equals pi, x equals pi, and I'm told that z is 0 because it's on the xy plane. So what values do I have? Well, the z values go from 0 to the sine of y. The y values go from y equals x to y equals pi. Right? Because if you see this point here, pi is 0, that must mean we go from y equals x to y equals pi. And then the x values simply go from 0 to pi. All right, so you can draw it out on the figure here if it makes it a little bit easier to see. There's your y equals x. So in the y direction, you're going from x to pi. Right, there's your pi. in the y direction. The x's go from 0 to pi, and then the z's go up until you get to the sine of y. Great. What am I going to do with this? Well, I'm going to integrate, but my f of x, y, z is really just 1. So I'm going to set up a triple integral. If I'm trying to find the volume, I'm going to integrate 1 dz dy dx, where the z's go from 0 to the sine of y, the y's go from x to pi, and the x's go from 0 to pi. And you notice I chose to put the z's first, then the y's, then the x's. All right, when we integrate with respect to z, what are we really doing? The integral of this with respect to z is just z evaluated at the sine of y and at 0. So this will give me just the sine of y. Really, then, I could have just put the sine of y and integrated it dy dx, and it would have given me, in this case, the same thing. All right, let's do the next step of integration. We'll go from x to pi of the sine of y dy. Right, the antiderivative of sine is negative cosine, so I get negative cosine of pi minus a negative cosine of x. So the cosine of pi is negative 1, so negative negative 1 is positive 1, plus the cosine of x. And now I'm going to integrate that from 0 to pi. Right? The next step says integrate from 0 to pi of 1 plus the cosine of x with respect to x. Right, so now the antiderivative of 1 is x. The antiderivative of cosine is going to be sine. Evaluate at pi and at 0. Right, so this gives me pi plus the sine of pi minus 0 plus the sine of 0. And would you look at that? Clearly that's all 0. The sine of pi is also 0, so my answer is just pi. All right, so that's the volume of that solid. All right, here's another volume of a solid. I'll set this up. Let's see how far we want to go into solving it. So the parabolic cylinder is y equals x squared. The plane that it intersects is z equals 3 minus y, so that's the plane that goes this way. And z equals 0 is the other boundary, so that's how we know that it sits flat on the xy plane. What are our values going to look like? Well, if we were to look at the parabolic base of this thing, where would it start and where would it end? Well, the z values will go from 0 to 3 minus y, because basically it's sitting right here, right? There's my 0, there's my z, the 3 minus y. So the z values go from 0 to 3 minus y. How about the y values? The y values start at x squared, right? If I'm taking the y values, they're going to be these slices over here. So they start at x squared. But how do I know where they stop? Well, come back up here to that z equals 3 minus y. What happens if z is 0? If z is 0, then I end up with y equals 3, right? Because then 3 minus y is equal to 0, where y is equal to 3. So while we're on that plane, this here is our flat boundary on the other side. That's y equals 3. So the y values will start at x squared. That's going to be the lowest value. And it's going to end at 3. That's the highest value. Great. Now how about the x's? Where do the x's go? Well, they start on the end over here, right? That's one x value. And they end on the other side over here. What are those values? Well, if the parabolic cylinder is y equals x squared, then if y is 3, I get 3 equals x squared, or plus minus the square root of 3 is equal to x. So the x values go from negative square root of 3 to positive square root of 3. All right, again, if we're finding volume, we're going to integrate 1 as our function. That's our f of x, y, z. I'm going to leave those limits of integration there. And so I'll end up with 1, 2, 3 integrals of 1. And then what order do I want to do this? Let's do it dz, dy, dx. So the z's go from 0 to 3 minus y. The y's go from x squared to 3, and the x's go from negative root 3 to positive root 3. All right, when I integrate this first piece with respect to z, then I just get 3 minus y, right? Because I'll get z evaluated at 3 minus y and at 0, which is 3 minus y. Great. Now let's do the integration with respect to y. So now I'm going to integrate from x squared to 3 of 3 minus y with respect to y. That will give me what? 3y, because I tack on a y for each one, minus y squared over 2, evaluated at 3 and at x squared. So when I put the 3 in for y, I get 9 minus 9 halves, and then minus, replace that y with an x squared, and so I get 3x squared minus x to the 4th over 2, because when I put an x in for this y, x squared in for that y, I get x squared squared. All right, so what's 9 minus 9 halves? That's the same thing as 18 halves, so I'm going to end up with a 9 halves minus 3x squared minus x to the 4th over 2. Now that has to be integrated with respect to x from the negative square root of 3 to 3, square root of 3. All right, so I'll find the antiderivative. I'll leave it to you to throw the values in because, yeah, they're going to get funky because we're going to end up with odd powers. So I'll end up with 9 halves minus 3x to the 3rd over 3 is just x to the 3rd, and that will give me a minus, actually give me a plus because I was minus. That should be a plus. X to the 5th over 5 times 2, which is 10, evaluated at the square root of 3 and at the negative square root of 3. If you want to work that out, you should end up with 24 square root of 3 over 5, but I think you get the idea. This is Calc 3. You've been integrating these single variable functions for, well, at least a couple of semesters now. All right, let's take a look at one more. This one says find the volume of the solid bounded by, I've got some x bounds, I've got some z bounds, and I've got a function. So when I go to set this up, I'm going to try to keep the most complicated part on the inside. So I'll integrate first with respect to y, because that's the part that has a function. You realize the other two are just constants. So I'll first integrate with the y values going from 0 up to e to the negative z. All right, that's my y values. The x values, we were told, go from 0 to 2. So why not put those next? The x's go from 0 to 2, and then the z values go from 0 to 1. All right, so when I set this up, it's going to be a triple integral of 1. We said the y's are going to come first, then the x's, then the z's. Y's go from 0 to e to the negative z. The x's go from 0 to 2. The z's go from 0 to 1. Right, when I do this first integration with respect to y, I'll end up with e to the negative z, right? Because that'll give me y evaluated at e to the negative z and at 0, which is just e to the negative z. All right, now we've got to integrate from 0 to 2 of e to the negative z with respect to x. Well, all that does is tack on an x. So I end up with x e to the negative z evaluated at 2 and at 0, except 2, don't forget, is an x value, and so is 0. Oops. So that'll give me 2e to the negative z minus 0. Right, for my last trick, I'll integrate 2e to the negative z with what? With respect to z from 0 to 1. And now when I do that, don't forget that it pops out a derivative of the exponent, so I end up with 2e to the negative z times negative 1. If it makes it more comfortable, you can always write it as negative 2 over e to the z, and then evaluate that at 1 and at 0. Don't forget, both of those values will yield answers, right? Just because there's a 0 in this case doesn't mean it goes away. You'll get negative 2 over e to the first minus a negative 2 over e to the 0. So you end up with negative 2 over e. E to the 0 is 1. So that plus 2. All right, there's my answer. That's triple integrals, just like double integrals, but with one more.